Hello again. We're going to begin this section or this module by going over a few exercises from chapter 1, section 1.4, just to give an idea of what you're expected to know. So exercises, this is just a sample for you. I always recommend that you go over all exercises if you have the time. There are some examples that are more relevant than others, but the experience gain, even if you don't get the exercise, you just think about it, it's very useful to understand the material. It's going to be very positive for you. Starting with exercise 1.4.1, so this is exercise in general, but we're going to be covering exercises from the book now, exercise 1.4.1. What does it say? It says that, well, it asks you to recall that I stands for the set of irrational numbers. Actually, it's stated here that you should recall this, that I stands for that, but I actually don't recall that was ever introduced. It was just mentioned in passing, but it was never actually defined as the set of irrational numbers. Nevertheless, maybe it didn't look well. But okay, so in fact, so make sure that we know what I mean by this. In mathematical terms, I is the real numbers minus the set of rational numbers. So that's the set of irrational numbers. We actually know there are way more irrational numbers than rational numbers. If not, then the set R would not be complete. And after this, we are asked to show a bunch of properties that you should know how to prove on your own. But so show that if A, B, R, and Q, then AB and A plus B are elements in Q, so elements of Q as well. B, show that, now this is another property, that if A is in Q and T is another number in, say, the rational numbers, if A, you pick a rational number, and T an irrational number, then A plus T is in I, and AT is in I, but of course this is only true as long as A is not equal to 0, because, well, then if A is equal to 0, no matter what you're multiplying by, it's going to be 0. So that would certainly be rational. So here there's a sort of an additional information, or lack thereof. That you have to think about. So part A Well, problems can be, it's what it says in the book, can be summarized by saying that Q is closed under addition and multiplication. Can we say the same thing about the rational numbers? I mean, to be more specific, what you should be looking into, and this is what they give you right after this question, is so given two irrational numbers, can you always say that the product is going to be rational or irrational? Or their sum? Do you always obtain an irrational number when you add irrational numbers? Or do you always get a rational number? Or neither of those things are true? Okay, so these are the questions for this exercise. There are 3 questions for exercise 1.4.1. So, let's try to come up with the solutions together. I mean, I know that you are uh, probably watching this, I mean, sometime, hopefully Monday or Tuesday. But, so what is the correct way of thinking about this? Okay, so you have an idea for part A. For part A is something that really doesn't require you to think anything. Just use the definition of a rational number. Okay, so you're given 2 rational numbers, and you're to show that their product or in their sum is going to be a rational number as well. So what are rational numbers? So this is just for part A. So it's just chasing definitions. So from the definitions, or from the definition actually of rational numbers, A, B belong to Q, if and only if there are numbers in Z. So I'm gonna call these numbers P, Q, R, or we're just gonna name P1 just to make it less confusing. P1, Q1, P2, Q2 in Z. So this is the definition of rational numbers. Those are numbers that can be written in the form P over Q, where P and Q are in Z, and where the denominators are non-zero. So you have to trust the fact that your definitions are going to give you most of the problems, and you're going to be able to prove most things just by blindly following the definitions and see where it takes you. So once you understand what you're asked to do, so what the problem is actually asking you to do, say you want to show that something is a rational number, so that means that I must be able to write it in this form. You must be able to write it as a fraction where the numerator and the denominator are both integers. Once you do that, okay, well then, of course it's going to be true because I'm going to be adding fractions, so of course I'm going to be getting another fraction where both numerator and denominator are integers. Okay, so again, first write down what you're asked, in mathematical terms, what you're asked to show, and after that write down what you are starting from, so your assumptions. So you need to know your definitions very well, not just some vague intuitive notion or some intuition, just using your intuition, but exactly what it says in mathematical terms. Okay, so we know, okay, so in Q different from zero, such that if not, this has nothing to do with A nor B, such that A is equal to P1 over Q1, and B is equal to P2 over Q2. Right, so this is the given information. So A and B are both rational numbers, and now you're going to add them and multiply them, and then you're going to see that they're rational numbers as well. And so how we proceed, so where A times B, remember the rule for multiplications of rational numbers. Thus you just need to multiply the numerators and the denominators. And what are the important points here? So when you multiply integers, you obtain another integer. So this is in Z, right? And when you multiply non-zero integers, then you get an integer that is not zero. So this means that this whole thing is then in Q. Right, going back to the definition, so you wrote AB as some integer over a non-zero integer, and that's it. That's it. That's all you have to show. Now for A plus B, well, remember you can simple cross multiply and say that this is the same as P1 times Q2 plus P2 times Q1 all that divided by Q1 and Q2. But then again, the numerator is in C, so it's an integer. You're multiplying two integers, P1 and Q2, so you get an integer, and you're multiplying the integers P2 and Q1, so you get another integer, and then you're adding them together to obtain yet another integer. We already saw that Q1 and Q2, when we multiply them, we get another. When we multiply them together, we get another integer, which is non-zero because neither Q1 or Q2 are 0. So this whole thing is again in Q. Okay. So this is part A. This is all you need to show. You just need to verify the definition and use the fact. The information you transform the information you're given into mathematical terms using the definitions. Now for part B, you're given now an element in Q and an irrational number. Okay, so A, what do you know? A is P over Q. Remember to write down the information you're given, so this is in Q. T is an irrational number. So how do you know that this is not so what can you say about A plus T? A plus T is some P over Q plus T. In fact, you don't need to use this information yet. It's just that, you can simply appeal to part A. But I want to show you exactly how this works. So this is supposed to be rational. Well, is it? Well, if it were a rational number, we would know that this could be written as some P bar over Q bar. Well, let me just use some other notation. So let me just go back here and use again P1 and Q1, P2 and Q2. Some P2 over Q2. Q2, all of this in Q. For P2 and Q2 are integers and Q2 is non-zero. But this would mean then that P1 over Q1 plus T would be equal to this P2 over Q2, and when we will be able to subtract P1 over Q1 on both sides and get that T is equal to P2 over Q2 minus P1 over Q1, and this is the same. I mean, we could actually just cross multiply here, but I want you to pay attention to something. This is how we reduce it to the previous case. So this is plus minus P1 over Q2. This is in Q. This is in Q. So this whole thing is in Q by part A. Okay, so then this is a contradiction. This is a contradiction, right? Because we say that an irrational number is a rational number. An irrational number t, by hypothesis, is in Q, is a set of rational numbers, but this cannot be the case. I mean, an irrational number cannot be a rational number by definition, because the rational numbers is a set of real numbers that are not rational numbers. Then similarly, if P1 over Q1 T would belong to Q, implies there would exist a P2 over Q2 in Q such that P1 over Q1 times T would be equal to P2 over Q2. And here we have to be a little bit careful, and this is, I mean, and pay attention to where our hypothesis here plays a role. So we would have this, right? So we can multiply by the inverse of P1 over Q1, so namely Q1 over P1. And when can we do that? Just give you a couple of seconds to think why this is not, I mean, this is something where we need to pay attention. Try to think about what could go wrong. Why can we just not multiply by something? For this to be defined, P1 must be not equal to what? Cannot be equal to 0. Oh, so that's a problem. Except that it's not a problem because we're assuming that A, the rational number, is not equal to 0. And A is equal to 0 if and only if P1 is equal to 0. So the rational number A is equal to 0 if and only if the numerator is equal to 0. on the numerator, so if and only if p1 is equal to 0. And since we're assuming that this is not the case, so say the AT is in I, so it's an irrational number as long as A is not equal to 0. So we're trying to show that this is an irrational number provided P1 is not equal to 0. Because if it were equal to 0, then that would imply that A is equal to 0. So this fraction here makes sense, and we can multiply on both sides, and we can get then that T is equal to P2, Q1 times P2 over P1 times Q2, which is in Q. And this is again a contradiction, right? T is not in Q. So this is a contradiction. What is the problem? What did we assume that it was wrong? That this belonged to Q, that this was a rational number. So the only possibility here is that that this product here is in the irrational numbers, is an irrational number. Okay, so if we add rational numbers, so let's summarize. If we add rational numbers, we obtain rational numbers. If we multiply rational numbers, we obtain rational numbers. If we multiply one rational number and an irrational, you obtain an irrational number unless the rational number was equal to 0. In all other cases, the product of an irrational and a rational number would be equal to an irrational number. And if we add one irrational number and a rational number, then the result will be, the result of this addition. So when you add these two numbers together, you will obtain an irrational number. So that's the content of A and B. Now, we need to see what happens when you add irrational numbers and when you multiply irrational numbers. What can you say about these things? And that's the point of part C. Right? So, part C asks you to know if I is closed under addition and multiplication. But the answer is that you cannot really know. Okay, so how do you know this? How do you know that this is not known? Well, suppose S and T, so let's say with a few examples. You have to show this. I'm gonna leave this to you as a as an exercise. But so suppose that you pick, say, the square root of 3 and or the square root of say the square root of 3 minus the square root of 2. Well, let's make it easier. Because we already know that if we add an irrational number and a rational number, we obtain an irrational number. So let's pick the square root of 3 minus 1, and then the t to be the square root 3 plus 1. There's nothing in particular about these numbers. It's just that it's just to actually, in fact, it's just to show you that in general you should expect to have this kind of situation. For one case or the other. So if you want to obtain an irrational number, or if you want to obtain a rational number. So this is not, it's not very hard to come up with examples. So this number is rational. And this number is irrational as well. Why? Square root 3, if you remember the discussion at the beginning and in the first problem session, square root 3 is an irrational number. 1 and minus 1 are both rational numbers. They're integers. And what did we say? We say about adding an irrational and an irrational number in part B? Well, then when you do that, you obtain an irrational number. So this first number and the second number, S and T, are both irrational numbers because you're adding an irrational number to a rational number, or a rational number and an irrational number, however you want to look at it. But you obtain an irrational number. That's part A. That's part B of this very same question. So what now? S plus T is equal to the square root of 3 minus 1 plus the square root of 3 plus 1. The ones of course cancel out and you get 2 times the square root of 3. But this is a rational number again. 2 is an integer. So it's in particular a rational number. And this is an irrational number. So the whole thing again by part B of the same problem. We know that this is an irrational number. We're multiplying an irrational number times a rational number. So this multiplication turns out to be an irrational number. So it gives you an irrational number. Okay, so we have an example where we're adding two rational numbers and we're obtaining an irrational number. But what happens if we flip the sign of one of these things? Then we'll see. So for instance, now another example. So we say if you conjecture then whenever you add irrational numbers you obtain a rational number, that would be wrong. What if we consider then now S to be instead 1 minus the square root of 3 and T to be the same thing? I'm just going to write it slightly differently. 1 plus the square root of 3. Then S plus T would be equal to 2, which is a rational number. So what's the conclusion here? Can you say anything about the addition of two rational numbers? Can you always guarantee that the addition is going to be, the result of adding two irrational numbers is going to be either irrational or rational? No, you found an example where you added two rational numbers and you obtained an irrational number, and you also have an example where you added two irrational numbers and you obtain a rational number. So you cannot say that there's a rule for this. Each one of these things can happen, that when you add two irrational numbers you obtain an irrational number, or that you obtain a rational number. So both things are possible, and that's where things are. A similar reasoning shows you that this is also the case for the multiplication. So for multiplication, say we're going to do the same thing. So 1 over square root 3, which is going to be irrational, and the square root 3 for T. So as an exercise, I asked you to show then that this is an irrational number. This we already know that it's an irrational number. Yeah, just to help you out with this one, if you take the inverse of an irrational number, then there has to be an irrational number. Otherwise, you could write this on the other side. On the other side as a, this would be a rational number, and when you divide things, you obtain a rational number. So the square root of 3 would have to be 1 over a rational number, and 1 over a rational number is a rational number as well. So the same kind of contradiction we used before is going to give you that this is going to be an irrational number. So what happens when you multiply s times t? S times t is in this case 1, which is clearly a rational number. Okay, so when you multiply an irrational number and another irrational number, you may obtain a rational number. So what about then? What about multiplying two irrational numbers? I mean, in obtaining an irrational number, is that possible? Is it possible? Is it possible to obtain obtain an irrational number by multiplying two irrational numbers? I'll give you a couple of seconds to think about something. I mean, just using the same kind of reasoning that we used before for obtaining an irrational number here. You want basically the rational part to cancel. So is it possible? Well, yes. I mean, it is certainly possible to obtain an irrational number. So suppose you have the square root of 3 over 2, and t is the square root of 2. Then s times t would be equal to the square root of 3, which is an irrational number. Now the question is, of course, this is an irrational number. And why is this an irrational number? You know that square root 3 and square root 2 are both irrational numbers. But what about the square root of 3 over 2? Is that an irrational number? Well, I'll leave it to you as an exercise, but it follows the same kind of reasoning we apply to this kind of problem. Okay, so basically assume that the left-hand side is a rational number and perform all the operations that you want, and you'll obtain that this number here would have to be irrational. Otherwise, you obtain a contradiction. Okay, so you obtain basically that there's a number that is divisible by 2, and the other so the denominator is divisible by 2 and the numerator is divisible by 3, and then when you go back to all the operations you need to do, you obtain this, like when you show that the square root of 2 is irrational, you will be able to simplify the expression further, so the quotient further, but that would be a direct contradiction with the fact that, I mean, so you have to assume from the very beginning that the left-hand side, so the rational number you're expressing square root 3 over 2 as, is in its reducible form. So try to do that, and then that would conclude this problem. Okay, so we'll go over a couple more problems and try to see if you if you can try to work these problems out without looking at the lecture, and that will mean that you're understanding the material a little bit better, and hopefully this helps us moving forward.